actually today I would like to start with a new topic which is on flow through packed bed. Is it clear as to, in the case of multi-particle systems? Okay, so we kind of derive this, UT is, sorry, UP, that is the particle settling velocity under, hindered settling condition, goes as UT power epsilon power n. Right? Is that clear? Is that clear how we got this? Right? We basically said that U relative terminal goes as UT times epsilon times f of epsilon, right? We derived that. Then we said that UT, U particle, okay, under hindered settling, it goes as epsilon square into f of epsilon. We derived that. Okay, this was basically derived by bringing in the concept of the volumetric flow rate of the particles plus volumetric flow rate of the fluid should be equal to 0 because there is no net flow in the system, right? And then we defined couple of terms called as actual velocities and the superficial velocities. Okay, you can actually think about writing a very simple continuity equation. So your QP, which is the volumetric flow rate of the solids, goes as UP superficial, S for superficial, times A, which is the area of cross section that is available for the entire fluid particle system to flow, R, that is equal to UP times 1 minus epsilon, because times A, of course, right? There's A as well. Only thing I've done is I've only taken the area that is available for the particles to flow, right? Similarly, I can write UQF, which is the volumetric flow rate of the liquid, as U fluid superficial times A, that is equal to U fluid times A into epsilon, right? This basically comes from the couple of definitions of the superficial velocities and the actual velocities, right? Then we went on to say that this f of epsilon is a function which is typically less than 1, and there are different models that people have proposed, and according to one of the models, your f of epsilon was epsilon to the power of 2.5, right? We derived that. Therefore your UP comes out to be epsilon to the power of 4.5, and we said that this is typically applicable for your epsilon which is of the order of 0.9, or your phi of the order of about 10%, or a 0.1%, right? And there are a lot, people have done a lot of experiments to kind of verify some of these things, and I said that this value of n depends on the kind of condition that you're working with, right? Newton's regime, Stokes regime, and things like that. There's a very famous equation which is what is called as a Richardson Zaki, Z-A-K-I, I think, equation, in which what people did is they did a lot of experiments on hindered settling conditions, and they worked with a lot of particles of different types, and then they kind of showed that this exponent n is 4.65. okay, though according to theory it should be about 4.5, and experimentally people have shown that this value is typically slightly higher, and that, which is about 4.65. okay, and other thing that we did was we started talking about UPS by UT. Okay, that is a settling flux, okay, non-dimensional settling flux, and the way we did that was your UP is epsilon to the power of n times, right, UT, right? Okay, and therefore your UPS, okay, which is the particle settling velocity but the superficial velocity, right, goes as UP times 1 minus let me just quickly do that. Okay, it goes as UP times 1 minus epsilon, right? Therefore your UPS is going to be UT into 1 minus epsilon into epsilon power n, right? And we said if you were to plot this, okay, so it would, the function would go something like that, is what I had mentioned. Okay, this is actually plot of UPS by UT versus 1 minus epsilon. I did a mistake in the last class. It's not epsilon, it's 1 minus epsilon. It turns out I can get this point and this point just by differentiating this one a couple of times, right? So if I do that, so if I take this UPS by UT and if I differentiate it once, okay, d by d epsilon, if you do it, okay, what I will do is I will get this as 1 minus epsilon into n minus epsilon power n minus 1, okay, plus of minus 1 into epsilon power n is equal to 0 if I equate that to 0. Therefore, if I work this out, I would basically get an expression for epsilon as n divided by n plus 1. Okay, that is your this point. Okay, and if I do the double derivative and if I do it, basically this particular point comes across to be n minus 1 divided by n plus 1. Okay, and this is this particular plot is what I've drawn is for n is equal to 4.65, that is the Richardson-Zake equation. Okay, and it turns out this particular point corresponds to 0.177 and this point corresponds to 0.35. That means if I have this is 1 minus epsilon, or it's a concentration, right? Or you can think about this as a particle fraction, and if your particle concentration is less than 0.177, you will see some kind of settling behavior in your system, and then of course there is some region where you see some other settling region, and so basically depending upon the initial concentration that you work with, okay, the settling, if you were to do this batch settling experiments, you will see different behavior that I discussed in the last class, right? There's a type 1 settling or type 2 settling or something very different from these two. Everything depends on the initial concentration of the particle that you work with. Okay, and in the case of the other point that I wanted to mention is what is called as there are, when you do these settling experiments, you'll always have sharp interfaces. Okay, that's what I kind of showed in those batch settling experiments, right? So that means I could have a case where I have a uniform dispersion to begin with, okay, where everywhere the particle concentration is the same, but then at some point in time you would have a case where I have an interface, okay, and I could have a case where I have a clear fluid at the top and all the particles at the bottom, or in general I could have a case where the particle concentration is less here, concentration could be C1 here and the particle concentration could be a bit more here, right? So in such a case I can have a settling velocity associated with each of these phases. Okay, this could be UP1, you can take it as regime 1 or 2, and in this case the settling velocity is going to be UP2, and if your interface is moving down with the velocity UINT, that is the interface velocity, and I said you can think about writing a simple mass balance, which basically is UP1 minus U interface, okay, multiplied by your concentration. Concentration C1 in this case is 1 minus epsilon 1. You're basically expressing this in terms of the void fractions, right? Should be equal to UP2 minus UINT into C2, right? If you work it out, it turns out this basically will have units of mass per second, okay, because this is meter per second, right? And this is your concentration, volume fraction. Of course I can have the area multiplied on both sides, right? So basically this is a mass balance, which basically is telling you that if you want to have a clear interface, whatever the number of particles or the concentration of the particle that will reach the interface, the same number of particles have to go. Okay, so if you work it out, your UINT becomes UP1 C1 minus UP2 C2 divided by C1 minus C2. If I have a case where I have a clear fluid here and then all the particles are in the in the bottom regime, so one of the concentration is going to be 0, right? If you say that C1 is 0, that is in the top regime, so basically this gets cancelled, you basically get UP2 itself, right? So therefore when you do these settling experiments, when you are following the interface velocity, right, which is basically I said that, right, if you have different interfaces, there could be a case where some interfaces are basically falling as a function of time. There could be cases where the interface is rising as a function of time. All I need to do is get the slope, okay, that is you're plotting height versus time. I get this dH by dt, that is basically my interface velocity, and from that I have a way of calculating the settling velocity. Okay, so maybe we'll stop here at this point. So we have talked about different things in the previous lectures, right? We talked about settling of single particles, then we talked about how do we extend that to an aggregate of particles, and then again extension of the similar concept to cases where we have multiple particle systems, right? So now we'll talk about a concept called flow through packed beds. Okay, okay, and in a sense packed beds are kind of, it's a simple concept. What you basically mean by packed bed is you basically have a column, Okay, it could be a pipe, it could be, you know, a container, right? And this column is basically filled with, this is your column, okay, this is your packing material. Okay, now I had mentioned in a few lectures ago that the reason why the packed beds are used are because they want, you know, they provide us a way of improving the contact between two or more phases. Okay, I could have a case, you know, for example, say that, you know, I have a say a simple pipe, okay, hollow pipe, and in which, you know, I want to send two liquids, okay, like say you know, maybe uh, some methane, or you know, some liquid and a gas, for example. If I want to ensure a proper contact between the two, if I were to have a simple pipe without any of these obstruction, obstruction, so there's no proper contact between the two phases, right, two fluid phases. Okay, so therefore the one of the main advantages of using these packed beds is, you know, they essentially ensure that if you have a two phase or three phase, systems, they give you a way of improving the contact between different phases. Okay, and people typically use this for cases where there's a gas liquid operation, or a liquid liquid, or a liquid solid. Okay, depending upon, you know, there are a lot of cases in chemical industries where you come across, you know, different fluids that are going to be, you know, you want them to be in contact, either liquid liquid, liquid solid, or gas solid. So in such cases, people make use of these devices to ensure that, you know, there's a proper contact between different phases. Okay, now, so this is again a schematic that I picked up. Okay, this is an example of a case where people have, this is an absorption column. Okay, again, typically what you'll have is, you know, some packing material in the pipe. There is some liquid that is coming in. There could be some gas that is coming out. You know, if your objective is to either, you know, take out, if you have a, if there's a gas, for example, if the gas has some trace amount of chemical, for example, mist, you know, or if there is some, for example, if I want to have a clean gas that I want to come out. Okay, if there is some unwanted gas that you want to separate out. Okay, one of the best way of doing this would be use of this packed bed. Okay, let it pass up through the column, and then, you know, use an appropriate liquid which basically takes out this unwanted, you know, material. Okay, and then it comes out at the bottom, and again you can, you know, subject it to whatever purification that you want to do. Okay, and people use them for the scrubbing or degassing operations. Okay, which is to remove traces of gas, vapors, or chemical mist. Absorption column, people use it for catalytic reactors. Okay, if you really want to, if you want to have a particular reaction that I want to occur over a solid surface. Okay, the best way of doing this would be, again, you pack them into these columns. Okay, and as you let either a liquid or a gas through this column, on the surface of these catalysts, you know, some reaction may occur, right? So yeah, as I said, right, they're used for distillation operations, a lot of mass transfer operations. You know, absorption is one example I talked about. Chemical reactors, separators. Okay, so these have very wide applications. Okay, and you will have a couple of experiments in the next semester to look at, you know, different aspects of flow through packed beds. Okay, so now before we go to the reason why we are interested in a packed column is because, like we talked about pressure drop in a pipe, right? Now if you have a pipe that is filled with, you know, particles, right? Again, now the fact that, you know, there's much more obstruction for the liquid to flow through, your delta P is going to be much larger compared to the, you know, case of flow through pipes, right? So the ultimate aim of some of the things that we're going to discuss is to look at how do we think about pressure drop through such systems, and we're going to think about some ways of analyzing, you know, flow through the packed bed, and, you know, how do we kind of correlate the pressure drop to different parameters, like, you know, the structure of the packing, you know, flow of the flow rate of the liquid, and, you know, few things like that is what we're going to do. Okay, so it turns out that, you know, so you know of a particular operation called filtration. Okay, which is some kind of it's a special case of flow through packed bed, right? Again, filtration, one of the simplest thing that you can think about, you know, when people do this coffee or tea at home, right? When you strain the coffee or the tea, okay, on the, you know, strainer, right, you have some solid bed that is, okay, initially it's a clean, you know, cloth or something like that. At some point in time, you know, as you start straining it, you have a bed of solid that forms, right? So ultimately, you know, the liquid starts flowing through the bed of solid that is formed on the surface, right? So therefore we're going to talk about filtration at some point. Okay, we're going to say that whatever working equation that we develop for packed beds, we can actually modify it to suit the need of filtration processes. We'll talk a little bit about that. Before we do that, I'm going to talk a little bit about what are called as packed bed internals. Okay, so let's look at the construction. Okay, so what you are seeing is a picture where there's a packed column. So this is two regions where there is particles that are kind of packed, right? This is solid particles which are put in the column, and on the bottom you have a support grid. Okay, because I mean this grid is basically required because I want to hold the packing, right? If I don't have this grid, all these particles would fall off, right? So typically there's a support grid. It's typically a porous plate, and again people use different kinds of design to ensure that there's a proper flow of fluids through these through these columns. At the top, somewhere here and somewhere here, you have what is called as a liquid distributor or liquid redistributor. Okay, and the job of this liquid distributor is to ensure that there's a proper distribution of liquid across the entire packed bed. Okay, that's the job of these liquid distributors. And if you look at somewhere here, they have what is called as a liquid collector. Okay, and the job of this liquid collector is if you have a really long column, what may happen is that as it flows through, what typically fluid does is it wants to go through the least resistance path, right? It will find out some least resistance path, after some time. Of course, if you look at the top of the bed, there could be a proper distribution of the fluid because of these liquid distributors. Okay. However, if you go down the column, if the column is really high, this liquid takes some preferential paths. Okay, and these are the least resistance path. Okay, one of the way to avoid that would be you put in this liquid collector. Okay, the job of this liquid collector is it basically collects the liquid that is coming out down the packed column, and then it kind of feeds it to a liquid redistributor. Okay, so these operations, these kind of internals are really required to ensure that the flow rate across the different cross sections of the bed is kind of uniform, so that there's a proper contact between the fluids that you're trying to work with. Okay. Okay, so this is a different kind of liquid distributor. Okay, as I was mentioning, liquid distributor basically provide uniform distribution of liquid. Okay, and as I said, okay, if the height of the packed bed is very large, okay, there may be something called as a channeling. Okay, the channeling is what I said. When the liquid starts taking some preferential paths, that means there is a larger flow in one region of the packed bed versus the other region. Okay, that's when you have what is called as a channeling, and channeling can be avoided if you use these redistributors and things like that. Okay, so these are 4 different types of distributors people use. These are some kind of a porous pipes. Okay, this is a pipe through which the liquid is flowing, but there are regions where I let the liquid into the column. These two, this and this is what is called a notch type distributor. Okay, if you see this, right, there's a wedge kind of thing, right? If you look at these things, so there's the construction is something like this. Okay, it's a parallel channel like that, and then there's a notch. Okay, and basically you fill the liquid in this, these channels, and then through the notch the liquid basically comes down. Okay, that's the case here and here. Okay, this is an example of what is called a orifice, type of liquid distributor, which basically has porous, porous openings, right, and then through that the liquid basically flows. Okay, so these are what people typically use, and as I said, right, the objective of this liquid distributor is to ensure that to avoid channeling and to ensure that there's a improved efficiency, right? That's the whole point. Now I just want to define a few terms. Okay, first term that we're going to do is something called a porosity. All of you already know this concept, but I still want to do it quickly. Okay, so porosity, it's also called as a void fraction. Okay, void fraction or porosity, or people also call it as voidage. Okay, is defined as volume of the voids in the bed, okay, divided by the volume of the packed bed. Okay, and volume of the voids in the bed, I can basically write it as volume of the bed minus volume of the solids, right? And therefore I can write this as 1 minus volume of the solids divided by volume of the packed bed. okay, and volume of the solids divided by volume of the packed bed, we know that is the packing fraction of the solid, right? So that's a typical definition of the voidage. Now, so how do we find voidage in the packed bed? Okay, so I say that I have a column. Okay, I'm going to say that, hey, look, I have a column that is filled with, and this is my packed bed. Okay, and I want to find out what is the voidage. Okay, what do you think is the, can you think of some ways by which I can measure the void fraction? Okay, experimentally you can think of a couple of different simple ways of doing it. Okay, what you do is, so you take an empty column, okay, and with a packed bed, what you do is you start going on filling the fluid. Okay, you start going on filling the fluid. So what fluid is going to do is, if I have a support plate, okay, and it will start occupying all the pores in the bed, right? The liquid that I'm going to add is going to basically occupy all the pores in the fluid. Now what you do is, if you have some way of collecting that fluid and then measure its volume, okay, if I know if it's a cylindrical column, if I know the length and the cross sectional area, right, I can get the volume of the bed, and if I measure what is the volume that I've collected, right, that is one way of doing it. Other ways of doing this would be, you finish up your packed bed experiment, okay, and ensure that your liquid is basically kind of filled up to the height of the packed bed, and we basically drain the fluid, right? So you can different ways of doing that. Now it turns out that porosity is one of the really important parameters that is kind of help in the kind of achieving. So when I talked about this efficiency, right? Efficiency. When I mean by what I mean by efficiency is that if you are able to ensure a better contact between the different phases, that's when I can say that the efficiency of the operation that I'm looking at, whether it's reactions or whether it's mass transfer operation. That's when that's what I'm looking for, right? To ensure improved efficiency, one of the parameters that you can play with is porosity. Okay, can you think of ways by which I can play with the porosity of the bed? So I have a packed column, it's filled with solids. Okay, now what are the different ways by which I can manipulate the porosity in the bed? You can change the dimensions of the particle. Okay, that's one way of doing it. So he is saying, what he's trying to say, let me just go back. Okay, so this is a okay. So what you're seeing here is dP by dt. Okay, where dP is the particle diameter, and dt is the if you have a packed bed, you can think about it as a diameter of the column in which the particles are put. Right now, so what you're looking at is two columns, epsilon for spheres. Okay, I'm already giving the second hint. Okay, this is epsilon for cylinders. Okay, now when you say dP by dt is 0, what does it mean? Okay, that basically means I have a really large column, okay, whose diameter is much larger than the diameter of the particle that are basically being used for making the packed bed, right? Okay, in such a case, your epsilon is 0.0 is 0.34, right? This value is very close to so if you have a spherical particle, you have something called a maximum random packing density, right? That means if I have a column, I pour the particles into the column. If all the particles in the bed, right, if they arrange in a random configuration, right? Okay, so it turns out that maximum random packing density is roughly of the order of 0.64, right? Therefore, the closest that you can get, if you really work with, ideally this should be 0.36, okay, but the closest that you get if you really take a very large diameter column, and if you put in the particles such that the particle diameter is much smaller compared to the diameter of the column, right? So you can achieve 0.34, but you can clearly see that if I go on if I go on increasing the the diameter of the particle, it turns out this porosity basically increases, right? Does it make sense? Because let's think about a simple case, right? If I have a column and I'm going to fill in the column with exactly the same diameter particles, right? I'm sure in this case the whatever volume that is available for the liquid is very, very little, right? Okay, so one of the way of doing this would be basically I can play with the diameter of the particle to the diameter of the column. But the other ways of doing this would be by using packing materials of different types. Okay, either you can work with regular particles, you can work with like say spherical particles or cylindrical particles, for example, or ellipsoids. Okay, you can work with particles of different shapes, or people have kind of designed different types of packing material itself. Okay, what you're looking at is this A. Okay, is a case of what is called as a Raschig rings. These are basically, yeah, go ahead. No, when you say volume of the packed bed, okay, this is the volume of the. So if I have a like say that I have a container, a cylindrical pipe. Say that the packing that I have filled it is up to say length L, for example. Okay, and if the diameter is D, right, that pi d square by 4 times L is your volume, right? That's the volume of the packed bed for me. Okay, it's not just the volume of the just the packing itself. When I say volume of the packed bed, so therefore, so in the example that we saw, so what I can do is I can take a column of some dimension and I can fill it up with particles of different sizes. That's one way of doing it. Okay, so the other way of, I mean, the same one of the ways of expressing exactly the same experiment that I said, right? I fix the column, I take particles of different sizes, right? One of the way of expressing that would be I basically express it as a ratio of dP by dL, right? That's what was basically done. Yes, yeah, it will. I think so. Basically, no. What this basically tells you, as long as if you were to do, you work with any combination of your particle and the the column. So as long as this is actually I've taken from one of the books. Okay, so the idea is as long as you maintain this ratio, the value would be typically close to 0.64. I mean, or the other way of doing this would be say that I have like say a column which is like say 100 centimeter diameter. Say that I'm basically taking 0.1 centimeter packing, for example. Okay, now if I do an experiment where I kind of increase the size of this by twice, so say I take 200 centimeter, and if I also take so in both the cases you would get a similar packing density. Okay, so yeah, that's the point. Okay, so this is something called a Raschig ring. So you can think about them as hollow cylinders, right? This is something called as a Lessing rings. Okay, so now if you look at, so for example, if I look at this and this, right? In terms of the shape, they are very similar. But only thing is, in between, I basically have another, basically a kind of a rectangular this thing, right? So now, if I compare these two, this would definitely offer me a much more solid surface that is available for any contact, right? Right? If I look at this and this case, okay, the fact that I have an additional a region there, so I basically have more solid surface available for any operation that I want to do. So people have using Raschig rings, Lessing ring. This is something called a Burl saddle. Okay, something called a Burl saddles. Okay, and this is what is called as a Paul ring. Okay, this is PALL ring. These two are PALL rings, right? And this is something called as a Nutter ring, Nutter. Okay, these are different names that people have. These are all industrially used packings of different shapes, and as you can clearly see, it is becoming more complex shape. Like if you go from A to F, for example, the shape becomes much more complicated, right? And the reason is that that will again help you in playing with your solid fluid surface areas, right? And so another way of, so like we talked about this dP by dt as a parameter for playing with your porosity. Okay, the other way of playing with the porosity is basically use packing material of different types. Okay, the Rastrick rings, Lessing rings. Okay, so if you play with some of these things, so you'll right. So I have a table which is not the porosity. I just wanted. Okay, I don't seem to have it. Okay, so maybe I had something here. Oops. I thought, okay, no, I had it here, right? So if you look at Rastrick rings, right, it turns out the porosity that I can reach is larger. Okay, so if you take Burl saddles, the typical porosity that you get is about 0.60. Okay, and again, if you use Burl saddles, okay, the typical porosity that you will be getting will be in this range. But now compare it with spheres, for example. You see, for the case of spheres, if I really take a very small diameter particles, okay, the porosity that I can have is about 0.34. Even if I increase the, if I play with the this dimension, okay, maximum I can go is up to 0.55. But however, if you use different shaped packing material, I can see that basically there's a more porosity, right? And more porosity would be good for a better efficiency of the operation or a better fluid particle contact. Yeah. So these are the Rastrick rings and the Burl saddles are the shapes. So basically, if you go back here, right, this is your Rastrick ring. Okay, this is your Burl saddles. Correct. Yeah. Correct. Yeah. So what you do is when you make a packed bed, right? As I said, packed bed is basically a column filled with the particles, right? Now the particles, I have a freedom of choosing whatever particle that I'm working with. Of course, if somebody is working with like say a catalytic reactor, I would have to use a packing material that is a catalyst that you want to use for a particular reaction, right? Or if I want to basically use an inert packing, okay, that means these are not participating in any reaction. If the objective is only to improve the liquid fluid liquid gas contact, for example, okay, I would like to have a much more surface area that is available, right, or more porosity, for example. So in such cases, what you do is you use one of these packing materials. So I can basically play with the porosity. That will also help you in regulating the pressure drop through the packed bed. Okay, plus it will also ensure a efficiency increase in the efficiency of the operation. Okay. So any other ways of doing this? So I said you can play with the particle and the column diameters, and I can play with the porosity. I can play with different objects of different shapes or different complex geometries, and I can play with epsilon that way. Any other? Yeah, you have a question? So these are basically, okay, let me go back. Okay, here I showed that in this image it looks like a sphere, right? I have put in a spherical particle in the column. Okay, instead of that I can use a Rastrick ring, right? I can use a Lessing ring, right? So that was actually your column like that, but with a right, I can use that. I can use Burl saddles. Okay, any of the packing shape that you saw, I can actually replace that, this spherical particle that you're seeing here, I can replace with any of these things, and that will help me in regulating your epsilon. Okay, that will help me in regulating the solid fluid contact. Okay, and it will also help me in regulating the efficiency of the operation. Okay, yeah. So any other methods of regulating epsilon? Yeah. No. Yeah. No. When you say more porosity, okay, what does it mean to you? So essentially, the volume, okay, that is available for the fluid is more, right? Now, when the volume that is available for the liquid is more, okay, if I say that, I'm using a liquid gas operation, okay, of course the part of this, the fractional voidage that is available, there will be liquid and the gas, right? The more the volume that is available, there's more contact between the gas and the liquid, right? In that sense, regulating porosity is a way of, I mean, people go for more porosity because, if you want to really improve the efficiency of the operation, I would definitely like to have more porous. Mhm. Correct. No, like I gave an example where if I have a pipe, right? Okay, I let the liquid and the gas flow through the column. Okay, when people talk about this two-phase flow in the columns, um, people talk about. Let me just go back. Okay, when you talk about two-phase flow, oops, okay, let me just go back here. Okay, so when you talk about two-phase flow, for example, say that I have a pipe. Okay, I want to have liquid 1, or say, let's say fluid 1 and fluid 2 that is flowing through the column, okay, through the pipe, for example. Okay, what do you think would be how would the flow look like? Or let's say two immiscible liquids, liquid 1, liquid 2, they are two immiscible. Say, but I would like to have a proper contact between the two. But people talk about something called a stratified flow, in which I have liquid 1 flowing above maybe and liquid 2 flowing below, depends on the density of the fluid. So there's a 2, right? That's one way of doing it. Think about it. The other way of doing this would be, people talk about slug flow, okay, in which you have, your liquid 1 could be here, and liquid 2 will be outside, right? This is liquid 1, okay, so it basically goes this, right? Now if you look at these two cases, the liquid contact actually happens here, right? You're only at the interfaces when there's liquid contact. If I look at this slug flow, there's a little bit better contact because I'm able to break the stream into maybe these slugs, okay. But however, your liquid contact is still limited. Now if I, what is the best way to ensure that there's a larger kind of a interaction between the two fluids, okay. When I say interaction, not the the interaction in terms of the molecular interactions, but I would like to have a proper contact between the two, okay. But the best way of doing this would be using these devices where you can ensure that there's a better interaction. So, why do you say the less porosity, more the break? So I mean, say you can't think of so in this case, are you talking about porosity in this case? Why would you talk about porosity in this case? Because if I look at this, your entire column is filled with the liquid. So in that sense, there's no pores as such, right? I wouldn't say, would you really call it as break the fluids? No, I mean, you have just like a liquid flowing through a column. You should imagine that there's also a liquid flowing through a bed of solids. Okay, there are channels available for the liquid to flow through. Okay, now as it flows through, if I have one or two different fluids, okay, and it'll have it'll basically give more chance for the liquids to interact. Let it put in that way. Yeah. Yeah. Okay, so the other way of doing this would be looking at something called as a random packing versus structured packing. Okay, so if you take a column, you just pour your particles into the column. Okay, they pack in a particular way. Okay, and typically, if you, again, there are ways, there are actually kind of prescription as to how you should fill the packing into your column. Okay, and if you follow some procedures, you will basically end up with a truly random packing. Okay, and other way of doing this would be what is called as a structured packing. Okay, in which I have some predefined way in which the solid material is basically arranged. Okay, so I'm basically showing you the random packing of spherical particles here and the structured packing of spherical particles here. And as you can clearly see that in this case, that typically the porosities that you can achieve would be of the order of 0.36. If you do a random packing here. But however, if you look at this case, packing fraction is more, if I assume a particular kind of packing, right, your porosity is going to be, right. So basically the other way of playing with your porosity is go for random versus structured packing. People typically don't use particles and then do a structured packing. So what is done in the okay, so I'll come back to this point. So these are some kind of structured packing that people use. So these are what you have is you basically have structure which are either made of some polymer, or it could be made of some metal, okay, in which you basically if you look at these pictures, right, the solid part, right, the solid material that make the packed bed, there's a particular way in which it is constructed, right, okay, and that forms the solid in the packed bed, okay, and whatever pores that you see here, right, there is a pore spaces through which the liquid basically flows through, okay. So and the idea of going for random versus structured packing is that the surface area available for the liquid and the void space I can basically manipulate, right, like just the point that I made earlier. So I can basically play with the void edge, plus also I can play with the surface area that is available for the fluid contact by using these devices, okay. So we have defined this parameter called sphericity, and it turns out if you look at when we are going to talk about this delta P, which is the pressure drop through the packed bed, the sphericity also becomes important parameter, okay. We have defined what it is already. It is defined as SP by Vp, okay, of a SP by Vp of a sphere divided by SP by Vp of the particle, right, and SP by Vp for the sphere is 6 by dP, and SP by Vp that's for the particle, okay, that's your sphericity. And if you see here, if you look at spherical particles or cubes or short cylinders, your sphericity is 1, okay. And if you go for Raschig rings, okay, this is L is equal to dP, that is your if you have this Raschig rings, right, that's your cylinder kind of thing, so that's your length and that's your dP, right. So if L is equal to dP, if it's a short cylinder, Raschig ring, so I can play with these dimensions, I can actually play with the porosity, right, 0.53 in one, 0.58 in one case, 0.33 in the other case. Burl saddles typically have a sphericity of 0.3, okay, and these are the kind of industrial packing that people use. And people also work with for example, you can have a column in which you may be working with some kind of sand particles, or you could be working with coal dust, for example, okay. In such cases again your sphericity would vary, okay, and there are ways by which, as we discussed in the class, there are ways by which I can basically calculate sphericity, right. Other term similar to the multi-particle system, there's a concept called superficial velocity, which is basically defined as the volumetric flow rate of the fluid through the column divided by the cross-sectional area, that is your Q by A. It is also called as a empty tower velocity, okay. Superficial velocity is also called as a empty tower velocity. This is the velocity of the fluid through the column when there is no packing, okay. That is your Q. I know if I have a column, if I have a way of measuring what is the flow rate through the column, and if I know what is the cross-sectional area, that Q by A is what gives you the superficial velocity, right, also called as a empty tower velocity. But the average velocity of the fluid through the pores is basically your superficial velocity divided by epsilon, right, because epsilon will tell you what is the cross-sectional area that is available for the liquid to flow through, right, okay. That's the actual velocity, or the average velocity of the fluid through the pores, okay. Yeah, so that's about it, okay. I just wanted to briefly introduce you to the concept of packed beds today. We have talked about what are packed beds, where are they used. We talked a little bit about packed bed internals, that there are liquid distributors, liquid collectors, and some concepts like that. We defined a few parameters, void edge as a sphericity. We talked a little bit about superficial velocity, and we also talked about different types of packing and different types of packing material, and what are the different methods by which people manipulate your porosities and the fluid solid contact area that is available for the fluid. Okay, we will stop here. On Monday we'll have we'll start talking a little bit about pressure drop through the bed. Okay, what we do is we're going to take the analogy of flow through pipes, and we kind of apply that to the flow through pack. Okay, that's what we'll do on Monday. Yeah, thanks.